So the purpose of curve sketching, which is what the handout is that Nancy posted on Facebook for us, is about learning to use the derivative and in some cases the second derivative to analyze the behavior of a given function. Okay. And it's sort of hard to imagine when you have really good technology that we're not just going to graph the function on a calculator and figure out what it's doing. Okay. That we're trying to think about how we approach problems like this, thinking about not having a calculator in your hand. And what can we learn about the behavior simply by analyzing the function? Okay. So what I want to focus on are what pieces of information I'm going to learn from specific acts that we're going to do in order to answer the set of questions. So let's look at example number 5 or problem number 5, which gives us that f of x is equal to x squared plus 5x plus 4 divided by 3x squared minus 3x minus 6. Okay. And you're asked to come up with a whole bunch of different pieces of information. We need to figure out what the domain is. Okay. We need to determine what the range is. Okay, I kind of put those two things in different categories, certainly. I need to know where the x-intercepts are. I need to know where the y-intercept is. Okay. If there is one, where is it? It will be singular. You could have, I suppose you could have infinitely many x-intercepts, certainly not greater than the order of the function itself, but you could have multiple x-intercepts. You could have no x-intercepts or y-intercepts. That's entirely possible, but those are things we're considering. Then I want to know where it's increasing. I want to know where it's decreasing. I then want to figure out where the vertical asymptote might be. Horizontal asymptotes. And then finally, I want to know if there are any skew asymptotes. Notice I'm putting out here, it's rare. Okay, it's not a common occurrence for that to happen. And then I want to know if there are any holes in the graph. Okay, think about them being like chug holes driving down the street. That's what I want to know. Okay. And in fact, these are going to be places where the function has a discontinuity in its graph, but it's just a singular point. And so if you were graphing the function, you might not even see that the hole exists. That's what I'm looking for. Okay. Okay. So let's start at the top. To find the domain of the function, you want to set the denominator of the fraction equal to 0. Okay. But to start with, maybe let's factor the numerator and the denominator. Okay. So this will be x plus 4 times x plus 1 divided by, this is going to be 3 times, so I get 3 times x squared minus x minus 2. And that factors into x minus 2 times x plus 1. Okay. So I now have my denominator factored and my numerator factored. And so what I should notice is that x plus 1 is common to the numerator and the denominator. Which means that it's going to be a removable discontinuity. At the point where x equals -1. Okay. The function is not defined at that point. But it's not going to be it's not going to be a large issue for us. Okay. Meaning I've got a numerator and denominator both going to 0 at that location. So I'm simply going to remove it from the domain. It's going to present with a hole in the graph. Now, the domain is going to be all x values except where x equals 2 and -1. So that's going to look like this. I'm going from negative infinity to -1. I'm going to skip -1. I'm going to go to 2, and I'm going to then union that up with 2 to infinity. That's all x except for -1 and +2. Now the range we'll come back to, because maybe we're going to take some limits and try to figure out what the range is actually doing. Okay, so now x-intercepts. These are the locations where the numerator is equal to 0. Okay, meaning the function is going to cross the graph at that location. Okay. When I set the numerator, the resulting one, equal to 0, x plus 4 is equal to 0, which implies x equals -4 is an intercept. So the x-intercept is at the point -4, 0. It can't intercept at -1 because even though -1 is a 0 for the numerator, the function's not defined at that location, so it can't intercept the axis. Okay. The y-intercept is found from evaluating the function at 0. You're finding f of 0. The x-intercept technically is solved from f of x equals 0, but the reason I set the numerator only is because I know the denominator can't be 0 if this is 0. Okay, so I'm looking for f of 0, which I'm going to use my factored form because it will be easier. This is 3 times 4 divided by 3 times -2. I don't know why I have a 3 in the numerator. I shouldn't. So this is 4 divided by -6, which is -2/3. So the y-intercept is at the point 0, -2/3. That's where it's going to cross the axis. So now we're ready to start using calculus to answer some of these questions. Increasing and decreasing intervals are determined by the first derivative. So I want to use the quotient rule to calculate the first derivative. Remember, it's going to be the derivative of the numerator, which is 2x plus 5, times the denominator, minus the numerator, times the denominator's derivative, which is 6x minus 3. And I would divide the entire thing by the denominator squared. Now, I need to clean up the numerator. I'm not worried about the denominator very much because it's strictly positive. For any value of x, when I square it, it stays positive. So I'm not going to worry about the denominator right now. I'm going to worry and focus about the numerator. Okay. So I'm going to distribute. This will give me 6x cubed minus 6x squared minus 12x plus 15x squared minus 15x minus 30. And then I've got this quantity, which I'm going to write right below it. Kind of bad notation, but you get the idea. This will be negative 6x cubed. This will be negative 30x squared minus 24x. And then this -3 in this is going to make a +3 plus 3x squared plus 15x plus 12. And that whole thing is still divided by 3x squared minus 3x minus 6, the quantity squared. So gathering terms, those two cancel. I've got negative 6x squared negative 6 plus 15 minus 30 plus 3, all times x squared. So I'm going to mark those terms out because I've taken care of putting them together, plus negative 12 minus 15 minus 24 plus 15 times x. And then I have negative 30 plus 12 is negative 18. Still over 3x squared minus 3x minus 6, the quantity squared. Okay, so I have 15 and 3 is 18. Minus 30 is negative 12. So this is minus 18x squared minus 36x minus 18. All over. And now I'm going to factor this denominator because I'm in hopes that something good will actually happen. Okay. I know that 3x squared minus 3x minus 6 factors into 3 times x minus 2 times x plus 1. So that's 3 times x minus 2 times x plus 1, the quantity squared. So that'd be 2 of each one of those. So that's 9 and a square and a square. So now I'm going to factor the numerator. I'm going to take out the negative 18. I'm left with x squared plus 2x plus 1, which, by the way, factors. So this is going to give me negative 2 times x plus 1, the quantity squared, over x minus 2 squared times x plus 1 squared. So this is negative 2 times x minus 2, the quantity squared. So what do we know? Well, looking at f prime, what I notice is that it's negative for every possible value of x. This is less than 0 for all x in the domain. Now, why is that helpful? Well, because I know this thing is decreasing everywhere, okay? That's what this thing is telling me, is that I have a function that's decreasing for every possible value of x, okay? So its intervals of increase, there aren't any, and their intervals of decrease, well, this is the same as the domain, okay? Hopefully that makes sense about why that's true. Okay. So I'm going to start on another page because I kind of hate to erase stuff in case I need to come back and pick it up. But let's see what else I need to figure out. I need to know where the vertical and horizontal asymptotes are. That requires limits. Okay. So what I want to do is I want to take the limit as I get close to 1, actually negative 1, because I want to show that it's removable. And I want to take the limit as I get close to 2, okay, of my function that's factored. So I actually will just erase this part. I think that'll work really well. Let me take this off. Perfect. Okay, now I'm ready. So I know that my intervals of decrease, only if I get my pen back, are going to be for x in the domain of negative infinity to negative 1, union negative 1 to 2, union 2 to infinity. Okay. And there aren't any for increasing. So now let's tackle the vertical asymptote. Okay. Let's look at what happens as I get close to negative 1. These are one-sided limits. Hopefully you remember doing that from before. I'm looking at what happens as I get close to x coming from the left side of -1. So in other words, all values less than -1. This is x minus 2 times x plus 1 divided by 3 times, I got to look back, can't remember, x minus 2 times x plus 1, and this is x plus 4. Okay. And remember, you're looking for sign behavior or the ability to factor. We factor this out. This means I'm considering this. I now no longer have a discontinuity, so I can evaluate at -1. This gives me positive 3 over 3 times -3, which is going to give me -1/3. This tells me my function approaches the value of -1/3 as I get close to -1 from the left-hand side. I'm going to get the same result from the right-hand side. I don't even need to check it because I'm able to actually evaluate the function at that point. So I don't need to check it. So this is removable. The limit exists. The function doesn't exist at that. Notice f of -1 does not exist. But the limit as x approaches -1 of f of x is equal to -1/3. The function's not continuous, doesn't meet continuity, but this does meet removable. Limit exists, function doesn't. Okay. Now, let's consider what goes on when x equals 2. Okay. The limit as x approaches 2 coming from the left of the reduced fraction. I don't need to worry about x plus 1, because it factors out. But I can no longer plug in 2. That won't work for me. Okay. So what I want to think about is what happens. So I'm on the left side of 2, which is like -1.999. Okay, that's what I'm thinking about. So -1.999 plus 4 is something positive. It's a positive number. I don't care what the number is, it's positive. When I look at the denominator, I'm approaching from 1.999 minus 2 is something very, very small and negative. This is small. And when you take something that is any number, and you divide it by something that is very, very small, you get something that is very, very large. Plus over minus is going to give me -infinity. This means as I get close to 2 on the left-hand side of it, I'm going to get close to -infinity. That's what this means. What happens when I get close to 2 coming from the positive side? Well, 2.1 plus 4 is something positive. 2.1 minus 2 is something very small and positive. And so this is going to go to positive infinity. This tells me there's a vertical asymptote at the point where x is equal to 2. So on my graph, when I graph this here in a minute, that's what I'm going to see is a vertical asymptotic line. On the left-hand side of 2, I'm getting close to -infinity, and on the right-hand side, I'm getting close to positive infinity. I call this Etch-a-Sketch behavior. If you've ever played with an Etch-a-Sketch, you know that when you move from the bottom of the screen to the top of the screen, you kind of get that drag line. That's what this looks like, is the drag line where the function's approaching it on either side. Okay? So we've got a vertical asymptote at x equaling 2. Now, horizontal asymptotes are also found by taking limits, but you're taking limits as you get close to infinity. Okay. So we're going to say that y is equal to the limit as x approaches infinity of, and I want to use my original function. I want to use this because it's easier. Okay. So I'm dealing with x squared plus 5x plus 4 divided by 3x squared minus 3x plus 6. When I'm taking limits going to infinity, I often use different rules, okay? Now, it may be the case that you've learned L'Hopital's rule. I don't know whether you have or not, so I'm going to approach this as if you haven't learned L'Hopital's rule, okay? If you've used it, you know that you're dealing with something that's indeterminate. So what I'm seeing here is that in the numerator, x squared is going to get infinitely large, and in the denominator, x squared is going to get infinitely large. I cannot and should not ever plug in infinity. What I want to do is I want to divide by the highest powered term in the denominator. This one. I want to divide every term by that term. So that's going to look like this. And I'm going to write it one more time as I really would write it. I would literally consider every term individually. This would be x squared over x squared, which gives you 1. 5 over x plus 4 over x squared divided by 3 minus 3 over x plus 6 over x squared. So here's what you're trying to have happen. You want every term in the denominator to either be a constant or you need it to be the form of this. Okay. Because when you allow x to get very large, these terms are going to go to 0. And the limit of a constant is always the constant. So this term's going to 0, so is this one, so is this one, and so is this one. And we're left with 1 divided by 3, which is the vertical asymptote. Horizontal asymptote. Plus or minus infinity in this case won't matter. Okay? Because x squared behaves the same way at both positive and negative infinity. So we don't need to worry about, will there be a sign change with the other version of infinity? There won't be. So I now know where the horizontal asymptote is. It's at y equals 1/3. There will not be a skew asymptote. There is only a skew asymptote if the numerator's order is larger than the denominator. It's the only time you'll ever have one that's skew. So now I'm ready to sketch my curve. I'm ready for the exciting part. Okay, we know where the hole is. There's a hole at x equaling -1 because it factored and removed. And now I'm going to use my little graph paper here to get us a decent sketch. And remember, this is about curve sketching. It's not about graphing. And there's a difference in curve sketching versus graphing. And here's the difference. That you're going to use minimal information to give yourself a general shape and behavior of the graph. Okay. So there's some things I'm going to make sure I actually plot. The vertical asymptote, I want to get it nailed. It needs to be exactly where it's supposed to be. I'm actually going to use a little larger scale than normal. This is 1. Here's 2. Here's 3. And I'll put 4 over here. And here's -1. Here's -2. Here's -3. There's 1. There's 2. -1. -2. Okay, I'm ready. There's a hole when x equals -1. But we did see that there was a limit when we got close to that. Okay. Our limit when we got close to -1 was -1/3. So I'm actually going to plot the point where that would be. And that would be right about here. So there's a hole in the graph. There's a point there. The limit exists, but the graph is not defined. Check the box. I got the hole placed. There's a horizontal asymptote at 1/3. So I'm going to dash line in my horizontal asymptote. This is where y equals 1/3. There's a vertical asymptote when x equals 2. There's the vertical one. Check the boxes. We're making progress here. Keep in mind, I cannot cross the vertical asymptote, but I can cross the horizontal one. Okay, it is entirely possible. This thing is decreasing everywhere. Okay, so I need to remember that that's what's happening. And I want to get my intercepts in the right place. 0, -2/3. So there's that intercept. And my x-intercept was at the point -4, 0. I guess I need to include that out here. So here is my intercept. Okay, now I've got to connect the dots, so to speak. I know from my limit behavior that when I get close to 2 from the left-hand side, it gets close to -infinity. This function has to be continuous. It's got a hole right there, but it's going to look like this. As I get close to -infinity, it gets close to this line y equals 1/3. And as I get close to 2 from the positive side, my function is decreasing and decreasing. It meets all the criteria for what we outlined as the behavior of this particular function. Okay. Okay, so I hope this helps. If you still need more than this, then have your mom shoot me an email, Facebook message, and I'll be happy to work another one of them for you and see if this gives you a little more clarity as to what's going on. Okay. Hope you have a better evening. Just relax, it'll get better.